Tonight, we are going to follow the quiet science of rain, clouds, and mist. There is no need to hurry. There is no need to remember every detail. You can simply listen, rest, and let the story of water move slowly in the background. Rain may seem simple at first. A cloud gathers, a drop falls, a window becomes covered in tiny silver lines. But behind this familiar sound, there is a slow and beautiful system moving all around the planet. Water rises from warm oceans. It drifts invisibly through the air. It gathers into clouds. It cools. It changes shape. And eventually, when the time is right, it returns to the ground as rain. Sometimes it falls softly onto leaves. Sometimes it taps gently against rooftops. Sometimes it disappears into soil, rivers, lakes, and quiet underground places. And sometimes, before it becomes rain at all, it waits near the ground as mist. A pale, low cloud, soft enough to hide a forest, thin enough to vanish with morning light. In this calm journey, we will explore how rain begins, how clouds form, why mist appears, why raindrops fall, and why the sound of rain can feel so peaceful when the rest of the world is quiet. You do not need to focus too closely. This is not a lesson to study. It is simply a slow walk through the science of water. A quiet look at the atmosphere above us, the ground beneath us, and the tiny droplets moving between them. So settle in. Let your breathing become easy. Let the sound of rain stay soft in the background. And let us begin with the water itself. The same water that moves through clouds, through rivers, through soil, through oceans, and sometimes through the quiet midnight air. Water is one of the most familiar substances on Earth. It is so familiar that we often stop noticing it. It waits quietly in a glass beside the bed. It gathers on a window during the night. It moves through pipes beneath the floor. It rests in the soil beneath a garden. It shines for a moment on a leaf after rain. And far away, beyond the rooms and streets and small human places, it stretches across the planet in oceans. Vast, dark, moving. When we hear rain at night, we are hearing only one small moment in a much larger story. A drop touches the glass. Another follows it. A thin silver line begins to move downward. And it may feel as if the rain has simply arrived from the sky, but the sky is only one part of the journey. A raindrop does not truly begin inside a cloud. Not completely. Before it was rain, it may have been invisible vapor. Before it was vapor, it may have been part of the surface of the sea. Before that, perhaps it moved through a river, or rested underground, or froze slowly inside a glacier, or passed through the stem of a plant. Water is always changing its place, and water is always changing its form. Liquid, vapor, ice, mist, cloud, rain, snow, dew, frost. The names change, the shape changes, the speed changes, but the water continues. Slowly, patiently, almost silently. Most of the water on Earth is held in the oceans. The oceans cover more of the planet than land does. They lie beneath clouds, storms, trade winds, moonlight, and sunlight. They receive rivers. They feed evaporation. They store heat. They help shape the weather. And they hold the largest part of the water that takes part in the quiet cycle we are following tonight. If you could look down at Earth from far above, the planet would appear mostly blue. Not because water itself is deeply blue in every small amount, but because the oceans are wide enough, deep enough, and vast enough to give the planet its color from space. Clouds would drift above that blue surface, white, gray, silver, and sometimes almost invisible. Some clouds would be thin and high. Some would be broad and low. Some would be building slowly above warm water. And somewhere beneath them, water would be moving from one form into another. This movement is called the water cycle. But the word cycle can make it sound too simple. In school diagrams, the water cycle is often shown as a neat circle. An arrow from the ocean to the cloud, an arrow from the cloud to the mountain, an arrow from the mountain to the river, an arrow from the river back to the sea. And those diagrams are useful. They help us see the basic idea. But the real water cycle is not a perfect circle. It is more like a quiet network of paths. Some paths are short, some are very long, some are visible, some are hidden, some water rises from the ocean and falls again within days. Some falls as snow and remains frozen for many years. Some sinks into the ground and moves slowly through spaces in rock. Some enters the roots of a tree. Some becomes part of a leaf. Some returns to the air before it ever reaches a stream. There is no single path that every drop must follow. A drop of water can have many possible futures. It may fall onto a rooftop and run into a gutter. It may land on warm stone and evaporate again. It may settle into moss. Tea may slide down a blade of grass. It may gather with other drops in a small puddle. It may seep through soil. It may join a tiny underground flow that no one sees. It may travel into a stream, then a river, then eventually the ocean, or it may pause. Water is very good at pausing. It can wait in a lake. It can wait beneath the ground. It can wait as snow. It can wait in ice. It can wait inside living things. And then, when temperature, sunlight, wind, and pressure begin to change, it can move again. The atmosphere holds only a small fraction of Earth's total water. Compared with the oceans, it is almost nothing. And yet, this small amount of atmospheric water has enormous importance. It is the water that becomes clouds, the water that becomes mist, the water that softens the outline of distant hills, the water that gathers on grass before sunrise, the water that falls as rain on a quiet roof in the middle of the night. The air around us can hold water in the form of vapor. This vapor is invisible. We do not usually see it. We only notice its effects. A humid evening, a foggy morning, a clouded window, a cool breath in winter air, the feeling of heaviness before rain. Water vapor is always present in the atmosphere, though the amount changes from place to place and from hour to hour. Warm air can generally hold more water vapor than cold air. This is one reason warm oceans are so important for clouds and rain. When sunlight warms the surface of the sea, some of the water molecules near the surface gain enough energy to leave the liquid behind. They rise into the air. They do not rise as tiny visible drops. They rise as vapor. No sound, no splash, no color, just a quiet transfer from sea to sky. This process is called evaporation. And evaporation is one of the main ways water enters the atmosphere. But the ocean is not the only source. Lakes evaporate, rivers evaporate, wet soil evaporates, rainwater on leaves evaporates. Even snow and ice can sometimes change directly into vapor, especially in cold, dry air. Plants also release water into the atmosphere. They draw water up from the soil through their roots. They move it through their stems, and then they release some of it through tiny openings in their leaves. This process is called transpiration. It is one of the quieter parts of the water cycle. A forest can send large amounts of water vapor into the air without making a sound. Leaf by leaf, tree by tree, a green landscape breathing moisture into the sky. Together, evaporation and transpiration help fill the lower atmosphere with water vapor. Over land, over forests, over lakes, over fields, over wetlands. Water is always moving upward in ways that are easy to miss. This is part of why rain connects places that seem separate. A cloud above a mountain may contain water that rose from a distant ocean, or from a forest, or from a lake, or from wet ground after yesterday's rain. A raindrop on a city street may have traveled farther than we imagine. It may have crossed hundreds or thousands of kilometers as vapor inside moving air. It may have risen, cooled, condensed, and joined a cloud. It may have drifted quietly across the sky. And only now, in this particular place, under this particular evening air, has it returned. Water is not only moving above us, it is also moving beneath us. When rain reaches the ground, not all of it stays on the surface. Some of it flows downhill, some enters streams, some gathers in puddles, some is taken up by plants, and some slowly sinks into the soil. This sinking movement is called infiltration. At first, water moves between grains of soil. Then it may move deeper, into sand, gravel, or cracks in rock. Far below the surface, water can collect in underground layers called aquifers. These hidden reservoirs are important sources of fresh water in many parts of the world. But they do not usually move quickly. Groundwater can travel very slowly, sometimes only a few centimeters in a day, sometimes less. Sometimes it remains underground for many years, or centuries, or even longer. This hidden water is part of Earth's quiet memory. Beneath forests, farms, roads, deserts, and towns, it moves through darkness. It does not follow the rhythm of waves. It does not fall with the sound of rain. It does not shine in sunlight, but it is still part of the same system, the same cycle, the same long movement. Some water is stored even longer in ice. Glaciers and ice sheets hold frozen water in enormous slow-moving masses. Snow falls year after year. It is pressed into layers. The layers become dense. The ice grows thicker, and the glacier begins to move, almost too slowly for the eye to notice. Inside that ice, tiny bubbles of ancient air may remain trapped. The ice can hold clues about past climates, past atmospheres, and old snowfall from times long before the present night. In this way, water can be both active and still. It can rush in a river. It can float in a cloud. It can fall as rain. It can sleep in ice. It can wait underground. It can rise from a warm sea. It can gather as mist in a valley. It can return again and again, always familiar, always changing. The living world is woven into this cycle too. Plants need water to grow. Animals need water to live. Microbes, fungi, mosses, insects, forests, wetlands, and fields all take part in the movement of moisture. After rain, soil becomes darker, leaves become brighter, the air may feel cooler, the scent of the ground may change. Tiny organisms become active, roots absorb what they need. Some water becomes part of life for a while, then, later, it returns, through breath, through leaves, through soil, through rivers, through the air. Rain, then, is not just weather, it is a meeting point. It is where atmosphere touches land, where cloud becomes river, where ocean returns to forest, where invisible vapor becomes something we can hear. When a drop lands on a window, it carries with it the history of movement. Not a history we can see directly, but a history written in changing forms. The surface of the sea, the warmth of sunlight, the lift of air, the cooling of a cloud, the pull of gravity, the quiet arrival on glass, soil, leaf, stone, or water. This is why rain can feel so old and so new at the same time. It has happened for billions of years, long before cities, long before roads, long before anyone listened to rain from inside a dark room. And yet each rainfall is also new. A new arrangement of air, a new gathering of vapor, a new cloud, a new path, a new return. Tonight, as we follow the science of rain, clouds, and mist, we can begin with this simple idea. Water does not belong to one place. It moves through many places. It connects them, the ocean and the cloud, the mountain and the stream, the tree and the atmosphere, the soil and the river, the glacier and the sea, the mist near the ground and the invisible vapor above it. All of these are different chapters in the same quiet story. Before rain falls, water must first enter the air. Tea must leave the visible surface of the earth and become something we cannot see. It must rise without wings, drift without sound, and wait inside the atmosphere. So next, we will look more closely at evaporation, the quiet process by which water becomes invisible, not gone, not lost, only changed and ready to rise. Evaporation is one of the quietest movements in the water cycle. It is happening almost everywhere, almost all the time. On the surface of the ocean, on the edge of a lake, on wet leaves after rain, on the skin after a shower, on dark soil warmed by morning light, and on tiny puddles that slowly disappear without making a sound. When water evaporates, it does not vanish. It only changes form. It leaves the visible world of liquid water and becomes water vapor, a gas so small and spread out that our eyes cannot see it. A puddle after rain may look still. A lake at dawn may look calm. The surface of the sea may rise and fall gently under the wind. But at the smallest scale, water is never completely still. Its molecules are always moving. They slide past one another, they bump into one another, they turn, vibrate, and shift. And some of them, near the surface, gain enough energy to escape from the liquid and enter the air. This is evaporation, a quiet leaving, a slow upward movement, a change from liquid into vapor. Most of the time, we cannot see it happening. We only notice what evaporation leaves behind. A towel becomes dry, a wet street becomes pale again. A glass of water left in sunlight becomes a little lower. A shallow puddle fades from the pavement. Morning dew disappears from grass. The water is not destroyed. It has simply entered the air. invisible, weightless in feeling, and ready to travel. Sunlight is one of the main sources of energy for evaporation. When sunlight reaches the surface of water, some of its energy is absorbed. The water warms. The molecules near the surface begin to move more actively. Some move slowly, some move quickly, and the quickest ones may break away from the surface. They leave the liquid behind and become vapor. This does not happen all at once. It happens molecule by molecule, quietly, continuously, across oceans, lakes, rivers, wetlands, soil, leaves, and rooftops. The ocean is the largest source of evaporation on Earth. It covers so much of the planet that even a thin, invisible exchange at the surface becomes enormous when spread across the whole sea. Every day, sunlight warms the upper skin of the ocean. Winds move across it, waves turn and fold the surface, and water molecules escape into the air. There is no single moment when the ocean decides to become cloud. There is only a constant rising, a fine invisible lifting, a soft movement from blue water into open air. If we could somehow see water vapor as it rises, the world might look very different. The sea would be breathing upward, lakes would be sending faint veils into the sky, forests would be glowing with invisible moisture, wet fields would be releasing yesterday's rain, rivers would be whispering water back into the atmosphere. But because water vapor is invisible, this part of the cycle is easy to forget. We see the rain when it falls, we see the cloud when it gathers, we see the mist when it hangs near the ground. But evaporation happens before all of that. It is a hidden beginning, the first quiet step toward a cloud. Temperature matters. Warm water usually evaporates more icily than cold water because its molecules have more energy. This is why a warm puddle disappears faster than a cold one. It is why steam rises from hot water. It is why tropical oceans can feed enormous amounts of moisture into the atmosphere. And it is why warm summer air often feels heavy with humidity. But evaporation does not require boiling. This is important. Water does not need to bubble and steam before it can enter the air. Even cold water can evaporate. Even ice and snow can slowly lose water to the atmosphere under the right conditions. At ordinary temperatures, at the quiet surface of a lake, water molecules are still moving. Some still gain enough energy to escape. So evaporation can happen gently. Without heat, we can see. Without steam. Without drama. Just a patient exchange between surface and air. Wind also matters. When air above the water becomes full of water vapor, evaporation slows down. The air is already carrying a great deal of moisture. But when wind moves that damp air away, drier air can replace it. Then more water can evaporate from the surface. In this way, wind helps carry water upward and outward. A breeze over the ocean. A cool current moving across a lake. Air passing over wet soil. Each one can help remove vapor from the surface and make room for more. This is why laundry dries faster in moving air. It is not only the warmth, it is the movement of the air. The moisture near the fabric is carried away, and more water can leave. The same idea works across the natural world. A wind across the sea, a wind through wet grass, a wind moving through the leaves of trees. All of it can help water return to the atmosphere. Humidity is another important part of evaporation. Humidity tells us how much water vapor is already in the air. When the air is dry, evaporation happens more easily. There is space, in a sense, for more vapor. When the air is humid, evaporation slows. The air is already holding a great deal of water. On a dry day, wet skin may cool quickly because water evaporates from it. On a humid day, the same water may remain longer because the air is already crowded with moisture. This is why humid weather can feel heavy. The air is not actually thick in a way we can see, but it is holding more water vapor, and our bodies can feel the difference. Evaporation is also linked to cooling. When the fastest water molecules leave a surface, they carry energy away with them. The remaining surface becomes a little cooler. This is why sweat can cool the body. Sweat forms on the skin, then some of it evaporates. As it leaves, it takes heat with it. The same principle happens on a larger scale over lakes, oceans, soil, and leaves. Evaporation moves both water and energy. It does not only send moisture into the sky, it also helps move heat through the atmosphere. This makes it a quiet but powerful part of weather. Water vapor is not just a passenger in the air. It carries energy. Later, when vapor condenses back into tiny droplets inside a cloud, some of that energy is released. This helps clouds grow. It helps storms form. It helps move heat around the planet. But for now, at this early step, everything is still quiet. The vapor is rising. The air is carrying it. The future cloud has not yet appeared. Plants also help send water into the atmosphere. This process is called transpiration. A plant draws water from the soil through its roots. The water moves upward through the stem. It reaches the leaves, and then some of it leaves the plant through tiny openings called stomata. These openings are far too small to notice with the eye, but they are important. Through them, plants exchange gases with the air. They take in carbon dioxide for photosynthesis. They release oxygen, and they also release water vapor. A single leaf may seem very small, but a forest contains countless leaves. Together, they can release a huge amount of water into the air. This is one reason forests can influence local weather. They do not only stand on the land, they breathe moisture upward. Quietly, leaf by leaf, branch by branch, tree by tree. In warm forests, especially after rain, the air can become rich with water vapor. Some of it comes from wet soil, some from streams, some from leaves, some from the plants themselves. The forest becomes part of the sky before it ever becomes a cloud. This idea can be very calming. A tree drawing water from the dark soil, a leaf opening slightly to the air, a tiny amount of vapor leaving the leaf. That vapor rising and mixing with other invisible water, then drifting, cooling, gathering, and one day perhaps becoming rain again. The water that falls onto a forest may later rise from that same forest. The cycle is not only ocean to cloud to rain, it is also soil to root, root to leaf, leaf to air, air to cloud, cloud to rain, rain to soil. A slow conversation between the ground and the sky. Evaporation can also happen from wet soil. After rainfall, the upper layer of soil holds moisture between tiny grains of mineral and organic matter. As sunlight warms the ground, some of that moisture evaporates. If the soil is exposed, it may dry more quickly. If it is shaded by plants, moss, or fallen leaves, the water may remain longer. Different landscapes release water at different speeds. A desert puddle may disappear quickly under sun and dry air. A shaded forest floor may hold moisture much longer. A wetland may keep sending vapor into the air day after day. A lake may release moisture slowly and steadily across its surface. Each landscape has its own rhythm, its own quiet way of returning water to the atmosphere. Even in cities, evaporation is everywhere. Rain falls on pavement. Water gathers along curbs. Rooftops become wet. Glass, metal, stone, and asphalt hold thin films of water. Then, as the air moves and the surface is warm, that water begins to leave. A city after rain is not only drying, it is breathing water back into the sky. The process may not look poetic at first. A wet road, a concrete wall, a drain, a rooftop, but the same science is there. Liquid water gaining energy, molecules escaping, vapor entering the air. The planet does not separate beautiful water from ordinary water. A raindrop on a leaf and a raindrop on pavement follow the same physical rules. Both can evaporate, both can rise, both can become part of a future cloud. This is one of the gentle truths of the water cycle. It connects everything without asking whether a place is wild or built, ancient or modern, quiet or busy. The water simply moves. When water vapor enters the atmosphere, it begins to mix with air. It may remain near the surface for a while. It may be lifted by warm rising air. It may be carried sideways by wind. It may travel across fields, hills, forests, cities, oceans, and mountains. It may stay invisible for a long time. There is no cloud yet, no raindrop yet, no mist yet, only vapor. But inside that invisible vapor is the possibility of all of them. A cloud is possible. A foggy morning is possible. A soft rainfall is possible. A snowflake is possible. A bead of dew is possible. All of these begin with water entering the air. The next step depends on cooling. Warm air can hold more water vapor. Cool air holds less. So when air carrying water vapor begins to cool, the vapor may eventually begin to condense. It may gather around tiny particles. It may become droplets. It may become visible. This is how the invisible begins to return. But before we reach clouds, it is worth staying for a moment with evaporation itself, because evaporation is easy to overlook. It is not loud, it does not fall on a roof, it does not roll across the sky in a gray shape, it does not glow like a rainbow, It is quiet, it is patient. It is the part of the story where water becomes almost ghost-like. Still present, but unseen. Still moving, but silent. Still part of the planet, but no longer held in the shape of a drop. And this quiet change is happening now. Somewhere, a wave is releasing molecules into the air. Somewhere, a lake is breathing softly into the morning. Somewhere, a leaf is opening its tiny pores. Somewhere, wet soil is drying slowly. Somewhere, rain that fell yesterday is beginning to rise again. Invisible, unhurried, changed, but not gone. This is evaporation, the quiet science of water becoming air. And as the vapor rises and drifts, it begins the next part of its journey. It moves into cooler places. It gathers with other invisible water. It reaches air that can no longer hold as much moisture. And slowly, the first signs of a cloud begin to form. A cloud begins before we can see it. It begins as invisible water vapor moving through the air. It may have risen from the ocean. It may have come from a lake. It may have left the surface of a leaf. It may have lifted from wet soil after rain. At first, there is no shape, no white edge, no soft gray shadow, no cloud floating above the horizon. There is only air carrying water in a form too small and spread out for our eyes to notice. But the atmosphere is always moving. Air rises, air sinks, air slides across land and sea. Air warms during the day and cools during the night. And as air moves, the water vapor inside it moves too. A cloud begins when air carrying water vapor cools enough for that vapor to change form again. The invisible becomes visible. The gas becomes liquid, not all at once, not as a sudden sheet of water, but as countless tiny droplets gathering around tiny particles in the air. This change is called condensation. Condensation is the quiet opposite of evaporation. Evaporation is water, leaving the liquid surface and becoming vapor. Condensation is water vapor returning from gas into liquid. It is the moment when invisible water begins to show itself again. We see condensation in many ordinary places. A bathroom mirror becomes foggy after a warm shower. A cold glass gathers beads of water on its outside. A window becomes misted on a cool morning. A breath becomes visible in winter air. In each case, water vapor in the air cools enough to become tiny liquid droplets. The droplets are small, very small, but together they scatter light. They make the invisible visible. A cloud is, in a way, a condensation that has happened in the sky. The air rises, it expands, it cools. The vapor inside it begins to condense, and the first tiny droplets appear. Softly, gradually, almost silently. One of the most important ideas in cloud formation is that rising air cools. Near the ground, air can be warmed by sunlight. Warm land, warm water, warm forests, and warm city surfaces can all heat the air above them. When air becomes warmer, it tends to become less dense than the cooler air around it, so it begins to rise. As it rises, the pressure around it becomes lower. There is less air pressing down from above. The rising air expands, and as it expands, it cools. This cooling is not because the air has entered a refrigerator. It happens because expanding air spreads its energy over a larger volume. The temperature drops, the air becomes cooler, and cooler air cannot hold as much water vapor as warm air can. This is a gentle but powerful rule of the atmosphere. Warm air can carry more water vapor, cool air can carry less. So, when moist air rises and cools, it may eventually reach a point where it is holding as much water vapor as it can. This point is called saturation. At saturation, the air is full of water vapor for its temperature. If the air cools any further, some of that vapor must leave the gas form. It begins to condense. Tiny droplets form, and a cloud starts to appear. The height where this begins is often called the lifting condensation level. It is a level where rising air has cooled enough for cloud droplets to form. Below that level, the air may be clear. Above it, a cloud may begin. This is one reason some clouds have flat bases. The air rises from below. It cools as it rises, and at about the same height, condensation begins. From far away, the bottom of the cloud may look almost like a soft ceiling, a gray-white layer where invisible vapor becomes visible droplets. But for condensation to happen easily, water vapor usually needs something to gather on. The atmosphere is not perfectly clean. It carries tiny particles, dust, sea salt, smoke, pollen, tiny bits of soil, microscopic material from plants, oceans, fires, deserts, and human activity. These particles are called aerosols. Some of them can act as cloud condensation nuclei. That means water vapor can condense onto them. The particles are tiny, but they are important. Without them, cloud droplets would have a harder time forming. A cloud droplet often begins around a speck so small that we would never see it alone. A grain of sea salt lifted from ocean spray, a dust particle carried from dry land, a microscopic fragment from a forest, a tiny seafloor drop. Around this little particle, water molecules begin to gather. One molecule, then another, then many more. A droplet begins. Not a raindrop, not yet. Cloud droplets are much smaller than raindrops. They are so small that they can remain suspended in the air. They drift with the movements of the atmosphere. They rise, they fall. They swirl. They collide, they evaporate, they form again. A cloud may look still from the ground, but inside it there is constant motion. Tiny droplets are moving and rising and sinking currents. Vapor is condensing. Droplets are evaporating. Air is mixing. Temperature is changing. A cloud is not a solid object. It is not a floating piece of cotton. It is not a container full of water. It is a living-looking pattern made of air, vapor, droplets, ice crystals, light, and motion. It has edges, but those edges are always changing. At the edge of a cloud, droplets may evaporate back into vapor. Inside the cloud, vapor may condense into droplets. The cloud grows where condensation is stronger. It fades where evaporation is stronger. This is why clouds can appear to build, stretch, thin, and disappear. They are not things in the way stones are things. They are processes. Slow, visible processes in the sky. When we look at a cloud, we are looking at a place where the atmosphere is changing water from one form into another. The shape of a cloud depends on many things. The temperature of the air, the amount of moisture, the strength of rising air, the direction of wind, the stability of the atmosphere, the landscape below. Mountains can lift air upward. Warm ground can make air rise. Cold and warm air masses can meet. Sea breezes can push moist air inland. Forests and lakes can add moisture to the lower atmosphere. Each situation can help create a different kind of cloud. Sometimes air rises gently over a wide area. This can create broad, layered clouds, soft gray sheets that cover much of the sky. Sometimes air rises in small, warm bubbles. These are called thermals. They can create puffy clouds with rounded tops, clouds that seem to grow like quiet towers in the afternoon. Sometimes air is forced upward by mountains. As moist air climbs a slope, it cools. Condensation begins. Clouds may form along mountain ridges, wrapping the peaks in mist and white layers. Sometimes two air masses meet. Warm, moist air may be lifted over cooler air. Large cloud systems can form. Rain may follow. But even when the weather becomes large and complex, the beginning is still small. Water vapor, cooling air, tiny particles, condensation, droplets. A cloud. One of the calmest ways to imagine a cloud is to think of it as a place where air has become cool enough to reveal the water it was already carrying. The water was there before the cloud appeared. It was hidden, transparent, mixed into the air. Then the air cooled. The vapor gathered. Light began to scatter from tiny droplets, and suddenly the sky had a shape. A soft white patch, a gray layer, a drifting veil, a rising tower. A cloud is water made visible by cooling. This simple idea connects the cloud to many other quiet moments. The fog on a bathroom mirror, the dew on grass, the mist over a lake, the pale breath in winter. Each one is a version of the same change. Water vapor becoming droplets, invisible becoming visible, air revealing what it carried. But clouds do not always form as liquid droplets. In very cold parts of the atmosphere, clouds may contain tiny ice crystals. High clouds are often made of ice. These crystals can be small, delicate, and spread out in thin layers. They can give high clouds a wispy, feather-like appearance. Lower, warmer clouds are more likely to contain liquid droplets. Some clouds contain both liquid droplets and ice crystals at the same time. This mixture becomes important later when we look at how rain and snow begin. For now, it is enough to know that clouds are made of tiny suspended water particles, liquid droplets, ice crystals, or both. They are small enough to stay in the air for a while. and numerous enough to turn invisible moisture into visible sky. You may wonder how a cloud can float if it is made of water. Water feels heavy in a glass. Rain falls to the ground. A bucket of water is difficult to lift. So why does a cloud stay above us? The answer is partly size. Cloud droplets are extremely small. They fall very slowly, so slowly that the upward and sideways motions of air can keep them suspended. Inside a cloud, air is moving, sometimes gently, sometimes strongly. Tiny droplets are carried by these movements. They do not simply drop like stones. They drift. They are lifted. They settle. They are lifted again. They evaporate and condense. A cloud remains in the sky because its droplets are small and because the air around them is moving. But this balance does not last forever. If droplets grow large enough, they begin to fall faster. If ice crystals grow heavy enough, they begin to descend. If the cloud continues to gather moisture, some of its tiny particles may eventually become precipitation. Rain, snow, sleet, hail. But before any drop falls, the cloud must first exist. It must gather itself from vapor. It must turn invisible water into visible droplets. And this begins with cooling. The cooling may happen high above the ocean, above a forest, along a mountain ridge, over a city after a warm day, or in a valley as evening air settles and loses heat. Sometimes, near the ground, the same process creates mist or fog. Fog is essentially a cloud close to the surface. The air near the ground cools, water vapor condenses, tiny droplets form, and the world becomes softened. Edges fade, trees become silhouettes, roads disappear into pale gray distance. The science is similar. The feeling is different. A cloud above us changes the sky. A fog around us changes the world we are walking through. But both begin with invisible water becoming visible. Both begin with condensation. If you watch the sky after sunrise, you may see small clouds forming as the ground warms. At first, the air is clear. Then small white patches appear. They grow, merge, and drift. Later, they may fade as the sun lowers and the rising air weakens. On another day, a layer of cloud may cover the sky from morning to night. On another, clouds may gather over mountains and remain there, while nearby valleys stay clear. Every cloud is a record of what the air has been doing. Where it rose, where it cooled, where it held moisture, where it found tiny particles to gather on, where droplets formed, where sunlight met them, where wind carried them next. Clouds are not random decorations. They are visible signs of invisible movements. A white cloud is a quiet map of rising air. A gray cloud is a deeper gathering of droplets and shadow. A thin high cloud is a trace of ice far above. A low mist is a cloud that has come down to touch the ground. This is the beauty of cloud science. It turns the sky into a readable place, not in a rushed way, not with urgency, but gently. A person can look upward and notice that the atmosphere is always riding, in vapor, in droplets, in light, in shade, in soft, changing shapes. The cloud that appears above the horizon may not last long. Its edges may dissolve, its center may grow, its base may darken. It may join with another cloud. It may stretch into a layer. It may vanish before sunset. But during its life, it tells a quiet story. Water rose, air cooled, vapor condensed, droplets formed, light scattered, and the invisible became visible for a while. So when we look at a cloud, we are not looking at something separate from rain. We are looking at rain before it is rain. We are looking at mist before it descends. We are looking at ocean water after it has risen. We are looking at the next part of the water cycle taking shape in the sky. A cloud is a pause between rising and falling, a soft gathering, a visible waiting. And inside that waiting, tiny droplets move through air. Most of them are too small to fall, but some will meet, some will merge, some will freeze, some will grow. And eventually, in the right kind of cloud, the first true raindrops will begin. Before that happens, however, clouds take many forms. Thin clouds, tall clouds, layered clouds, low clouds, clouds like veils, clouds like hills, clouds like soft gray blankets. Each shape tells us something about the air. And in the next scene, we will drift through the main shapes of clouds, slowly, one by one. Clouds have shapes because the atmosphere has structure. They are not placed randomly in the sky. Their height, thickness, texture, color, and movement all tell us something about the air that formed them. Some clouds are high and thin, some are low and gray, some are small and puffy, some spread across the sky in broad layers. Some grow upward into tall towers, and some carry steady rain for many hours. To understand cloud shapes, it helps to know a few old Latin words that meteorologists still use today. Cirrus means curl, or lock of hair. Cumulus means heap, or pile. Stratus means layer, or sheet. Nimbus means rain. These four ideas appear again and again in cloud names. A cirrus cloud is usually high, thin, and wispy. A cumulus cloud is piled, or puffy. A stratus cloud is spread out in a layer. A nimbus cloud is connected with precipitation. Many cloud names are combinations of these words. For example, cumulonimbus means a towering heap cloud that produces precipitation. Nimbus stratus means a layered rain cloud. Altostratus means a middle-level layer cloud. Altocumulus means a middle-level heap or patch cloud. The names may sound technical at first, but they are mostly descriptions. They tell us where the cloud is, what shape it has, and sometimes what kind of weather it may bring. Clouds are often grouped by height. High clouds usually form above about 20,000 feet or 6,000 meters, though the exact height depends on latitude and weather conditions. Middle clouds often form between about 6,500 and 20,000 feet, or about 2,000 to 6,000 meters. Low clouds usually form below about 6,500 feet, or 2,000 meters. Some clouds, especially large storm clouds, grow through more than one level. They begin low and build upward, sometimes reaching high into the atmosphere. Height matters because temperature changes with altitude. High clouds are usually colder. Many are made mostly of ice crystals. Low clouds are often made of liquid droplets, especially when temperatures are above freezing. Middle clouds may contain liquid droplets, ice crystals, or a mixture of both. This difference affects how clouds look. Ice crystal clouds can appear thin, fibrous, and delicate. Liquid droplet clouds often look denser, softer, and more rounded. Let us begin with high clouds. Cirrus clouds are among the highest and thinnest common clouds. They often look like fine white threads brushed across the sky. Sometimes they resemble feathers. Sometimes they form long streaks. Sometimes they appear as delicate hooks or curls. Because cirrus clouds form high in the atmosphere, they are usually made of ice crystals. The air there is very cold. The ice crystals are small and spread out. This is why cirrus clouds often let sunlight or moonlight pass through them. They rarely cover the sky completely in a dark way. Instead, they create pale marks at great height. Cirrus clouds can be signs of changing weather. When they appear in certain patterns and gradually thicken, they may indicate that a warm front is approaching. A warm front occurs when warmer air slowly moves over cooler air. As the warm air rises gently, high clouds may form first. Then, over time, middle clouds and lower clouds may follow. Rain may arrive many hours later, so a thin high cloud can sometimes be an early clue. Not a guarantee, not an alarm, just a soft sign that the air is changing. Another high cloud type is cirrostratus. Cirrostratus is a thin, high layer of cloud. It may cover much of the sky but remain translucent. The sun or moon may still be visible through it. Because cirrostratus is made of ice crystals, it can produce halos around the sun or moon. A halo forms when light is bent and reflected by tiny ice crystals in a cloud. The result can be a pale ring, wide and quiet, surrounding the light source. A moon halo on a cloudy night can be especially calm to look at. It is a simple, optical effect. Light passing through ice, geometry written softly across the sky. Cirrocumulus is another high cloud type. It appears as small white patches or ripples. Sometimes people describe it as a mackerel sky because the pattern can resemble fish scales. Cirrocumulus clouds are usually thin and high. They are less common than cirrus and cirrus. Their small repeated shapes often indicate waves or ripples in the upper atmosphere. The air is moving in patterns we cannot see directly, but the cloud reveals them. Next, we can move down to middle-level clouds. The prefix alto usually means middle. Altostratus is a middle-level layer cloud. It often appears as a gray or blue-gray sheet covering much of the sky. The sun may appear dim behind it, like a pale disk behind frosted glass. Altostratus can form ahead of widespread precipitation. It may be part of a larger weather system. At first, it may not produce much rain at the ground. But as the cloud thickens and lowers, it can develop into nimbostratus, a deeper rain cloud. Altocumulus clouds are middle-level patch clouds. They often look like rounded clumps, rolls, or small heaps spread across the sky. They are larger than cirrocumulus elements and usually have some shading. Because they are lower and thicker than many high clouds, they can look more textured. Altocumulus often forms when there is instability or wave motion in the middle atmosphere. On warm, humid mornings, certain types of altocumulus may suggest that thunderstorms could develop later in the day. Again, this is not a promise. Clouds are clues, not commands. They tell us about conditions: moisture, temperature, stability, wind, rising, motion. But the atmosphere is complex, and a single cloud type is only one piece of the larger pattern. Now let us come lower in the sky. Low clouds are often closer, thicker, and more connected to the weather we feel near the ground. Stratus clouds are low, layered clouds. They can cover the sky like a gray blanket. Their base is often fairly uniform. They may bring drizzle, light rain, or mist, but they do not usually produce heavy showers. A stratus sky can make the day feel quiet and muted. The sunlight becomes diffuse. Shadows become soft. Distant objects may lose contrast. Stratus clouds often form when moist air near the ground is cooled gently. They can also form when fog lifts. In fact, fog and stratus are closely related. Fog is essentially a stratus cloud at ground level. If fog lifts a little, it may become low stratus. If stratus lowers enough to touch the ground, it becomes fog. This is one of the clearest examples of how cloud categories connect to one another. They are not separate kingdoms. They are forms within a moving atmosphere. Stratocumulus clouds are also low clouds, but they have more texture than stratus. They often appear as broad rolls, patches, or rounded masses, usually with gaps between them. The sky may be mostly cloudy but still show breaks of blue. Stratocumulus is one of the most common cloud types in the world. It often forms in stable air with some low-level moisture and gentle turbulence. It may bring light drizzle, but it is usually not a heavy rain cloud. From below, stratocumulus can look like a ceiling made of soft gray stones. Not flat like stratus, not tall like cumulus, but broken, rounded, and layered. Cumulus clouds are among the most recognizable. They are the puffy white clouds often seen on fair weather days. Their bases are often relatively flat, their tops are rounded and bright. They form when warm air rises in small bubbles called thermals. As each bubble of air rises, it cools. If it cools enough to reach saturation, water vapor condenses into droplets. A cumulus cloud begins. The flat base often marks the height where condensation started. The rounded top shows where rising air continued upward. Small cumulus clouds can be signs of mild, pleasant weather. They may form during the late morning or afternoon as the ground warms. Then they may fade toward evening as the surface cools and rising motion weakens. But cumulus clouds can also grow. If the atmosphere is unstable enough, and if there is enough moisture, a cumulus cloud can build upward. Its top rises higher, its base may darken, the cloud becomes taller. This growing form is sometimes called towering cumulus, and if it continues to develop, it may become cumulonimbus. Cumulonimbus is the great vertical cloud of thunderstorms. It can extend from low levels of the atmosphere to very high levels. Its top may spread outward into an anvil shape when it reaches a stable layer near the top of the troposphere. Cumulonimbus clouds can produce heavy rain, lightning, thunder, hail, strong winds, and sometimes tornadoes. For our calm journey, we do not need to dwell on the drama. But scientifically, cumulonimbus is important. It shows what can happen when warm, moist air rises powerfully. Inside such a cloud, air currents can move upward and downward at high speeds. Droplets and ice particles collide. Water freezes, ice grows, precipitation forms. Electric charge can separate inside the cloud. The cloud becomes a large vertical engine, moving moisture and heat through the atmosphere. Compared with a thin cirrus cloud, a cumulonimbus cloud is enormous. One is a faint brushstroke of ice, the other is a tower of weather. Both are clouds. Both are made from water in the atmosphere, but they reveal very different kinds of air movement. Nimbus, the word for rain, appears in two important cloud names, nimbostratus and cumulonimbus. Nimbostratus is usually a broad, thick, layered cloud that produces steady precipitation. It often covers the whole sky in a dark gray sheet. The rain from nimbostratus is usually more continuous than showery. It may last for hours. It may arrive with a large weather system. It may fall gently or moderately, soaking the ground over time. This is the classic long rain cloud, the kind of cloud that turns a day soft and gray, the kind that makes rooftops shine, the kind that fills gutters slowly, the kind that can make a room feel quieter from inside. Cumulonimbus, by contrast, produces more intense and often shorter-lived precipitation, showers, thunderstorms, sudden heavy rain. The difference comes from the cloud structure. Nimbostratus is layered and widespread. Cumulonimbus is vertical and convective. Layered clouds often form from broad lifting of air. Convective clouds form from stronger, localized, rising air. This distinction is one of the most useful ideas in cloud science. Layered clouds suggest gentle, widespread lifting. Puffy clouds suggest rising bubbles of warmer air. Tall clouds suggest strong, vertical motion. Thin, high clouds suggest ice crystals at great height. Low gray clouds suggest moisture close to the surface. Once you know this, the sky becomes easier to read. You do not need to know every cloud, species, or variety. Even the basic forms can tell a story. High and wispy means ice high above. Low and flat means moist air near the ground. Puffy and growing means rising warm air. Dark and layered means deeper moisture and possible steady rain. Tall and towering means strong upward motion. The official cloud classification system includes more detail. There are 10 main cloud genera: cirrus, cirrostratus, cirrocumulus, altostratus, altocumulus, nimbostratus, stratus, stratocumulus, cumulus, and cumulonimbus. These genera can be divided into species and varieties based on shape, arrangement, transparency, and special features. Some clouds form lenses near mountains. Some form ripples. Some appear in waves. Some have modest pockets hanging beneath them. Some form trails behind aircraft. Some glow with color near sunrise or sunset. But for this first quiet journey, the main genera are enough. They give us a useful map. High clouds, middle clouds, low clouds, vertical clouds, layered clouds, puffy clouds, rain clouds. Each category gives us a way to understand what the atmosphere is doing. Imagine looking up on a calm morning. A few small cumulus clouds begin to form over land. Their bases are flat, their tops rounded. This tells us that the ground has warmed the air, and small thermals are rising. Later, perhaps, a sheet of altostratus moves in. The sun fades behind the gray-blue layer. This suggests broader lifting and more moisture at middle levels. By evening, the sky lowers into nimbostratus. Rain begins, not suddenly, but steadily. The cloud types have become a sequence. A slow change in the atmosphere. Or imagine a night with cirrostratus clouds. The moon is visible, but surrounded by a faint halo. The sky looks thinly veiled. The ice crystals in the cloud are bending moonlight. Far above the ground, the air is cold and moist enough for high cloud to spread. It is a quiet sign, a delicate one. Another day, stratocumulus may cover the sky in patches. The light shifts between gray and pale blue. The air near the surface is moist, but not rising strongly enough to make tall clouds. The weather may remain calm. The clouds drift like a broken ceiling. These examples show why cloud shapes matter. They are not only beautiful, they are information. Soft information, slow information, information written in water droplets and ice crystals. To read clouds is to notice height, shape, thickness, color, and change. A bright white cloud is reflecting sunlight strongly. A darker cloud may be thicker, so less light passes through it. A cloud with a sharp edge may be forming in clearer, more stable air. A fuzzy edge may show evaporation or mixing. A growing top suggests rising motion. A spreading layer suggests horizontal movement or stable air. Cloud watching is a gentle kind of atmospheric science. It requires no instrument at first, only patience. The sky does not explain itself loudly. It offers clues, a texture, a height, a shadow, a direction of movement, a slow change from morning to evening, and each cloud name is just a way of organizing those clues. Cirrus, high and wispy. Cumulus, heaped and puffy. Stratus, spread in a layer. Nimbus, carrying rain. The words are simple once they become familiar. They are not meant to make the sky more distant. They help bring it closer. When you know that cirrus is made of ice, a thin white streak becomes more interesting. When you know that cumulus forms from rising thermals, a puffy cloud becomes a visible trace of warm air. When you know that stratus is related to fog, a gray sky becomes a cloud lowered toward the ground. When you know that nimbus stratus brings steady rain, a dark uniform layer becomes the beginning of a long, soft rainfall. And when you know that cumulonimbus grows from powerful rising air, a tall distant cloud becomes a sign of deep vertical motion in the atmosphere. All of this begins with the same basic ingredients: water vapor, cooling, condensation, tiny droplets, ice crystals, air movement. The cloud shape is the result. The atmospheric writes the process into form. The thin line, the soft heap, the gray sheet, the dark rain layer, the towering column. And eventually, when a cloud becomes thick enough, deep enough, and full enough, some of its tiny droplets or ice crystals begin to grow. They collide, they join, they become heavier, and the cloud begins to prepare for rain. A raindrop begins long before it falls. Inside a cloud, there are countless tiny droplets of water. They are much smaller than the drops we see on a window or feel on our skin. A typical cloud droplet may be only about 10 to 20 micrometers across. A micrometer is 1/millionth of a meter. So these droplets are extremely small. Many of them are smaller than the width of a human hair by several times. A raindrop, by comparison, is much larger. A small raindrop may be around half a millimeter across. A larger raindrop may be 2, 3, or even 4 millimeters across. That means a raindrop is not just a slightly bigger cloud droplet. It is much larger in volume. To make one ordinary raindrop, a cloud needs to gather the water from many tiny cloud droplets. Sometimes hundreds of thousands, sometimes around 1 million. This is one of the key questions in rain science. If a cloud is made of tiny water droplets, why do those droplets not simply fall as rain right away? The answer is size. Cloud droplets are so small that they fall extremely slowly. Their weight is tiny. Air resistance is large compared with their mass, and the air inside a cloud is almost always moving. There are rising currents, sinking currents, small turbulent swirls, gentle mixing. Because of this, tiny cloud droplets can remain suspended for a long time. They do fall, in a sense, but so slowly that the moving air around them can easily keep them aloft. A cloud is not a still container holding drops. It is moving air filled with suspended droplets and crystals. For rain to form, some droplets must grow large enough to fall faster than the air can hold them. They must become heavy enough to begin a real descent. There are two main ways this can happen. One is the warm cloud process, often called collision and coalescence. The other is the cold cloud process, often connected with ice crystals, and often called the Bergeron process or the Bergeron-Findeisen process. Both can produce rain, but they work in different ways. Let us begin with collision and coalescence. This process is common in warm clouds, especially in tropical and maritime regions, where clouds contain liquid droplets and temperatures are above freezing through much of the cloud. Inside such a cloud, not every droplet is exactly the same size. Some are a little larger, some are smaller. Some form on larger condensation nuclei. Some grow faster because of local conditions. This difference matters. A slightly larger droplet falls a little faster than smaller droplets. As it falls through the cloud, it may collide with smaller droplets in its path. If the droplets stick together after colliding, they coalesce. They merge into a larger drop. The larger drop now falls even faster. As it falls faster, it sweeps up more droplets. It grows again. Then it falls faster again. This can become a kind of gentle chain reaction. A droplet becomes a larger droplet. The larger droplet collects smaller ones. The collected water makes it heavier, and the heavier drop falls more quickly through the cloud. Over time, if conditions are right, the drop becomes large enough to leave the cloud as rain. The process sounds simple, but it depends on many details. Droplets do not always collide. Air can flow around a falling droplet and carry tiny droplets aside. A collision is more likely if the falling drop is large enough, if the smaller droplets are in the right path, and if air movement allows them to meet. Even after collision, droplets do not always stick. Sometimes they bounce apart. Sometimes they temporarily join and then separate. Coalescence depends on surface tension, droplet size, electrical effects, turbulence, and the speed of collision. So rain formation is not just droplets bumping into each other randomly. It is a physical process with probabilities. Many collisions happen. Some lead to growth, some do not. But across the enormous volume of a cloud, even small probabilities matter. There are countless droplets, countless tiny paths, countless small encounters, and gradually, some droplets become large enough to fall. In warm tropical clouds, collision and coalescence can be very efficient. Moist air rises, cloud droplets form. Larger droplets begin collecting smaller ones. Rain can develop without needing ice. This is why warm rain can fall from clouds that are entirely above freezing. But in many middle latitude clouds, especially deeper clouds, ice plays an important role. This brings us to the cold cloud process. Many clouds contain regions where the temperature is below freezing. But interestingly, liquid water can still exist below 0 degrees Celsius. Tiny droplets can remain liquid even when the air is colder than freezing. These are called supercooled droplets. They are liquid water droplets at temperatures below freezing. They have not yet frozen because they need the right conditions or particles to begin the freezing process. In the same cloud, there may also be ice crystals. This mixture of supercooled liquid droplets and ice crystals is very important for precipitation. The Bergeron-Findeisen process depends on a difference between water vapor over liquid water and water vapor over ice. At the same temperature below freezing, the saturation vapor pressure over ice is lower than over liquid water. That sounds technical, but the idea can be made simple. In a cold mixed cloud, water vapor more easily deposits onto ice crystals than remains balanced with liquid droplets. So ice crystals can grow while nearby supercooled droplets shrink and evaporate. Water vapor leaves the liquid droplets and deposits onto the ice crystals. The ice crystals become larger. The liquid droplets become smaller. The ice grows at the expense of the supercooled water. This is one reason ice crystals are so effective at starting precipitation in cold clouds. As ice crystals grow, they may form snowflakes. They may collide with other crystals. They may collect supercooled droplets, which freeze onto them. This process is called rimming. If rimming continues, the ice particle can become graupel, which is soft, rounded ice. In strong clouds, ice particles can be carried upward and downward by air currents, growing as they move through different regions. Eventually, the ice particles become heavy enough to fall. If the air below the cloud is cold enough, they may reach the ground as snow. If they fall through warmer air, they may melt and become rain. This is very common. Much of the rain that reaches the ground in temperate regions begins as ice or snow high inside a cloud. It melts on the way down. By the time it reaches us, it is liquid rain. So a raindrop falling on a quiet window may have begun as an ice crystal. It may have grown in the cold upper part of a cloud. It may have fallen into warmer air. It may have melted, and only then become the liquid drop we recognize. Rain can have an icy childhood. This is one of the elegant details of cloud physics. The rain we hear may not have been liquid for its entire journey. The cloud decides its path through temperature layers, cold above, warm below, rising air, falling particles, melting levels, freezing levels. All of these shape what finally reaches the ground. The vertical structure of the atmosphere is very important. Imagine a cloud with cold air in its upper part and warmer air below. Ice crystals form high in the cloud. They grow. They begin to fall as they pass through the freezing level. Where the temperature rises above 0 Celsius, they begin to melt. If the warm layer is deep enough, the snowflake melts completely. It becomes a raindrop. If the warm layer is shallow, or if there is another cold layer near the surface, other forms of precipitation may occur, such as sleet or freezing rain. But we will return to those later. For now, the key idea is that rain formation often begins far above the ground, in a cloud where droplets and crystals are constantly changing. Another important part of raindrop formation is the motion inside the cloud. Clouds have updrafts and downdrafts. An updraft is air moving upward. A downdraft is air moving downward. In small, gentle clouds, these motions may be weak. In large convective clouds, they can be strong. Updrafts can keep droplets and ice particles suspended longer, giving them more time to grow. A particle that might otherwise fall may be carried upward again. It may pass through regions with more liquid water. It may collide with more droplets. It may collect more ice. Then, when it becomes too heavy, it begins to fall, despite the upward motion. This is especially important in tall clouds. The stronger the updraft, the larger particles can grow before falling. This is why intense storms can produce large raindrops or hail. But even in calmer clouds, gentle vertical movement helps shape the growth of precipitation. The birth of a raindrop is not only about gravity, it is about the balance between gravity and air motion. Gravity pulls downward, updrafts push upward, turbulence mixes particles, condensation adds mass, collisions add mass, evaporation removes mass, melting changes ice to liquid, freezing changes liquid to ice. A raindrop is the result of all these small processes, finding a temporary balance. Once a raindrop leaves the cloud and begins falling through air, it continues to change. Very small drops are almost spherical. Surface tension pulls them into rounded shapes. Larger drops are not shaped like the classic teardrop, often drawn in cartoons. A falling raindrop does not usually have a pointed top and rounded bottom. In reality, small raindrops are round. Larger raindrops become slightly flattened on the bottom because air resistance pushes upward as they fall. They can look a little like tiny hamburger buns. Rounded on top, flatter underneath. As a drop grows larger, air pressure from below can deform it more. If it becomes too large, it may become unstable and break apart into smaller drops. On Earth, raindrops rarely get much larger than about 5 or 6 millimeters across. Beyond that, the airflow around them tends to break them. So there is a natural limit to raindrop size. A huge falling sphere of water would not remain stable for long. The air would push against it, the bottom would flatten, the shape would wobble, the drop would split. This means rain is not made of identical drops. A rainfall contains many sizes: tiny drizzle droplets, small raindrops, medium drops, large drops that fall faster and strike surfaces more strongly. The sound of rain partly depends on these sizes. Small drops make soft, fine sounds. Larger drops make deeper taps and splashes. A shower with large drops sounds different from a misty drizzle. A steady rain sounds different from a sudden downpour. The physics of droplet size becomes part of the music of rain. Falling raindrops accelerate at first because of gravity, but as they fall faster, air resistance increases. Eventually, the downward pull of gravity is balanced by the upward drag of the air. At that point, the drop stops accelerating and falls at a nearly constant speed. This speed is called terminal velocity. Small droplets have low terminal velocities. They fall slowly. Large raindrops fall faster. A typical medium-sized raindrop may fall at several meters per second. Larger drops can fall even faster, though still limited by air resistance and breakup. This is why heavy rain can feel sharp on the skin, while drizzle feels almost suspended in the air. Drizzle droplets are so small that they fall slowly and can drift with light winds. Rain falls more decisively. The difference is not just poetic, it is physical. It is size, drag, gravity, and air movement. Drizzle usually comes from low clouds with very small droplets. The droplets are large enough to reach the ground, but much smaller than ordinary raindrops. They fall slowly and close together, often from stratus clouds. Rain usually involves larger drops and often deeper clouds. Heavy rain tends to involve even larger drops, stronger cloud processes, and more available moisture. Inside the cloud, the supply of liquid water matters. Meteorologists sometimes speak of liquid water content. This is the amount of liquid water contained in a volume of cloud. A cloud with very little liquid water may look visible, but may not produce precipitation. It contains droplets, but not enough growth is happening. A cloud with more liquid water provides more material for droplet growth. If the cloud is deep enough, moist enough, and dynamic enough, precipitation becomes more likely. Cloud depth is important too. A shallow cloud gives droplets less distance and time to grow. A deeper cloud allows particles to spend more time moving through regions of moisture, more time for collision, more time for coalescence, more time for ice crystal growth, more time for rimming, more time for the cloud to turn suspended water into falling water. This is why some clouds pass overhead without rain. They are visible, but not productive. Their droplets remain too small, while the air below is too dry, causing falling droplets to evaporate before reaching the ground. Sometimes, rain begins to fall from a cloud, but disappears before it reaches the surface. This is called virga. The rain is falling. but the air below is dry enough that the drops evaporate on the way down. So even after a raindrop is born, it may not survive the whole journey. The atmosphere can return it to vapor before it lands. In other cases, the falling drop reaches the surface. It lands on a leaf, a roof, a lake, a road, a field, a window. Its descent ends, but its cycle does not. It may flow, it may soak in, it may evaporate, it may freeze, it may join other water, it may begin again. But in this scene, we are still inside the cloud, watching the beginning. Tiny droplets, suspended in moving air, some larger than others, some falling a little faster, some colliding, some merging, ice crystals growing in cold regions, supercooled droplets giving vapor to ice, particles rising and falling in currents, gravity slowly gaining influence, the cloud preparing to release what it has gathered. A raindrop is not born in a single instant. It is assembled, molecule by molecule, droplet by droplet, crystal by crystal, collision by collision. It is the result of many small events occurring in a vast, moving cloud, and when it finally becomes heavy enough, it begins to fall. Not because the cloud has opened like a door, but because physics has tipped the balance. The drop is now large enough. Its fall speed is now great enough. The rising air can no longer hold it. Gravity takes over. The raindrop leaves the cloud and begins its quiet descent toward the world below. Rain is not only something we see, it is something we hear. And often, it is the sound that makes rain feel most familiar. A dark window can become a small instrument. A roof can become a drum. A leaf can become a soft surface for tiny impacts. A puddle can become a field of small rings and taps. When rain falls, each drop carries a little energy. The drop has mass, it has speed, it has shape, and when it reaches the surface, some of that energy becomes sound. The sound depends on the size of the drop, the speed of the fall, the angle of impact, the material it strikes, and the way that material vibrates. A drop falling on glass sounds different from a drop falling on soil. A drop falling on a metal roof sounds different from a drop falling on moss. A drop falling into a lake sounds different from a drop falling onto a dry leaf. This is why rain has many voices. It is not one sound. It is a collection of small sounds happening together. Thousands of drops, thousands of impacts, thousands of tiny vibrations in air. And because those impacts are slightly different from one another, rain creates a sound texture that feels rich but not usually sharp. It is irregular but not chaotic in a threatening way. It changes, but slowly. It repeats, but never exactly. This balance may be one reason rain can feel calming. The sound gives the mind something gentle to follow, without demanding attention. A single sudden sound can wake us. A door closing, a dog barking, a phone notification, a sharp voice outside. These sounds stand out because they are brief, distinct, and often meaningful. The brain notices them quickly. It asks, in a sense, whether something needs attention. Rain is different. Rain is continuous. It fills the background. It makes a soft acoustic layer. And this layer can help mask other sounds. Masking happens when one sound makes another sound less noticeable. If rain is falling steadily outside, small noises inside or outside a room may become harder to detect. The creak of a floor, a distant car, a faint conversation, the hum of a building. The rain does not remove these sounds. It covers some of their edges. It blends them into the background. This is one reason people often use rain sounds, fans, or noise machines while sleeping. A steady background sound can reduce the contrast between silence and sudden noises. In deep silence, a small sound can feel large. Against a soft, continuous background, the same sound may feel less important. Rain can act like a natural sound blanket, not blocking the world completely, just softening it. From an acoustic point of view, rain contains a wide range of frequencies. Different drop sizes and different surfaces create different tones. Small drops may create higher, lighter sounds. Larger drops may create deeper taps and splashes. Rain on leaves produces a soft, scattered texture. Rain on metal can sound brighter and more percussive. Rain on soil can sound muted. Rain on water can produce tiny plinks, rings, and low splashes. Together, these sounds form a broad spectrum. This is why rain is sometimes compared to white noise. White noise contains many frequencies at equal intensity. It sounds like a steady hiss. Rain is not exactly white noise. Natural rain is more complex and changes over time. Depending on the recording and the rainfall, it may resemble pink noise or brown noise more than pure white noise. Pink noise has more energy and lower frequencies than white noise. Brown noise has even more low frequency emphasis. Many people find pink or brown noise softer than pure white noise because they are less sharp in the high frequencies. Rain can contain some of this softer quality. It has high frequency detail from small impacts, but also lower and mid-frequency texture from surfaces, wind, water, flow, and distant resonance. This gives rain a layered sound, fine detail on top, soft body underneath, a steady middle. No single tone dominates for long. The brain can listen without needing to solve it. This is important. Some sounds ask to be interpreted. Speech asks to be understood. Music may ask to be followed. A sudden bang asks to be located. A repeating alarm asks to be stopped. But rain does not usually ask for a response. It is information, but not a command. It says that water is falling. It says that the outside world is wet. It says that clouds have released moisture. But for a person resting indoors, steady rain is usually not urgent. The brain can allow it to remain in the background. This may be part of its comfort. Rain is also predictable in a broad way. Not every drop is predictable. The exact pattern is random. But the overall sound remains stable. A steady rainfall has a kind of statistical regularity. Drops arrive at random intervals, but the total texture stays similar from moment to moment. This kind of sound can be soothing because it is neither too simple nor too complex. A perfectly repeating beep would become annoying. Complete silence can make small interruptions stand out. A chaotic sequence of loud sounds would be stressful. Rain sits somewhere between. It is varied enough to be natural, steady enough to be safe, detailed enough to fill the air, gentle enough to fade from attention. This combination is sometimes called stochastic sound, meaning it has random elements, but the randomness is bounded. It stays within a calm range. The rain becomes a soft field of small events. The mind does not need to count them. It does not need to predict each one. It can simply let them pass. There is also a psychological side. For many people, rain is associated with shelter. Being indoors while rain falls outside can create a sense of separation from the weather. The outside world becomes active. The inside space becomes still. The window becomes a boundary. Beyond it, drops strike glass, pavement, leaves, and roofs. Inside, the room may feel warmer, darker, and more protected. This contrast can make rain feel peaceful. Of course, not all rain is calming for everyone. Heavy storms, flooding, thunder, strong wind, or dangerous weather can create stress. Rain is not automatically peaceful in every situation, but gentle or moderate rain, heard from a safe place, often carries a different meaning. It becomes background, it becomes atmosphere, it becomes permission to slow down. The surface rain falls and changes the entire sound. On a window, the sound is close and delicate. Drops, hit, flatten, merge, and slide. Some impacts are tiny clicks. Some become soft streaks. Some combine into little streams moving downward. The glass itself vibrates only slightly, so the sound remains small and bright. On a roof, the sound can be broader. Tiles, shingles, metal, or wood all respond differently. A metal roof may produce a sharper, more ringing pattern. A tiled roof may produce a drier tapping texture. A flat roof may add the sound of water gathering and flowing. The roof turns rain into rhythm. On leaves, rain becomes softer. Leaves bend. They absorb some of the impact. Drops hit the upper surface, break apart, gather at the edge, and fall again. This creates layers of sound. First impact, small splash, drip from leaf to leaf, drop from branch to ground. A forest in rain is not just hearing drops from the sky. It is hearing water pass from surface to surface. Canopy to branch, branch to leaf, leaf to moss, moss to soil. The forest delays the rain, it filters it, it changes its sound. On dry soil, the first drops may sound soft and dusty. As the soil becomes wetter, the sound changes. Water begins to soak in. Small pits form. Mud softens. Air escapes from tiny pores. The ground receives the rain more quietly. On pavement, rain can sound brighter. The surface is hard. Drops break quickly. Water gathers into thin moving sheets. Tires may hiss. Gutters begin to run. Drains begin to murmur. A city rainfall has its own acoustic signature. Glass, concrete, asphalt, metal, leaves planted along streets, distant traffic, and water moving through channels all mixed together. On open water, rain has another sound. Each drop striking a lake or pond creates a small crater, a crown, and a ring. A tiny bubble may sometimes form under the surface. Some underwater sound studies have shown that raindrops can produce distinctive acoustic signatures depending on drop size. Small drops and larger drops interact with the water surface differently. To the ear above the surface, rain on water can sound delicate and continuous. To instruments below the surface, it can become a complex pattern of impacts and bubbles. Even this peaceful sound is full of physics. Impact, surface tension, air pockets, ripples, energy transfer, waves spreading outward. When many drops fall at once, these individual events overlap. The result is a sound field. No single drop is heard for long. Instead, we hear the combined effect of countless impacts. This is similar to how we see a cloud. A cloud is made of tiny droplets, but from far away we see one shape. Rain sound is made of tiny impacts, but we hear one texture. Many small events become one continuous experience. The intensity of rain changes the sound too. Drizzle is fine and soft. Its droplets are small. They fall slowly. They may seem to hang in the air. The sound of drizzle can be almost a whisper, especially on soft surfaces. Light rain is clearer. Individual taps become easier to notice. Moderate rain creates a steady wash of sound. Heavy rain becomes louder, denser, and more energetic. At some point, the sound may no longer feel calming. It may become too intense. The most relaxing rain sounds are often steady but not violent, present but not overwhelming, detailed but not sharp, full enough to mask the background but soft enough to let the mind drift. This is why many sleep recordings use gentle or moderate rainfall rather than severe storms. They are designed to create continuity, not excitement. The rhythm of rain is also different from the rhythm of music. Music often has deliberate structure, a beat, a melody, a progression, a beginning and an end. Rain has no melody in the usual sense. It does not ask us to follow a tune. It does not build toward a chorus. It does not resolve. It simply continues. This can be useful for sleep because the mind is less likely to become attached to a pattern. There is nothing to anticipate, nothing to remember, nothing to finish. The sound can remain open, a continuous background with no demand. Rain can also make indoor spaces feel quieter by comparison. The room may not actually be silent. There may be ventilation, a computer fan, distant pipes, a refrigerator, small movements in the walls. But rain changes how these sounds are perceived. It gives the ear a broad, natural reference point. Instead of listening into emptiness, the ear rests on a soft surface of sound. This is similar to why some people sleep better with a fan. The fan creates steady noise. The rain creates steady natural noise. The effect is not identical because rain has more variation and organic texture. But both can reduce the sharpness of sudden changes in the sound environment. There is also the question of attention. Attention is drawn to novelty, a new sound, a sudden silence, a pattern that changes sharply, a voice, a signal. Rain is full of microvariation, but it rarely changes in a way that demands immediate action. The brain can classify it as background. Once classified as background, it can fade from conscious focus. This fading is part of relaxation. The sound remains, but the mind no longer has to hold it. It is there, then it is not there, then it is there again. Not because it stops, but because the tension drifts. This is exactly what many people want from a sleep sound. Something gentle enough to occupy the edge of awareness. Something stable enough to trust. Something natural enough not to feel mechanical. Something soft enough to let go of. Rain meets these conditions very well, especially when it falls steadily. Especially when thunder is absent. Especially when the listener is indoors, safe, warm, and ready to rest. The calming quality of rain is not only emotional, it is acoustic, it is physical, it is statistical, it is environmental. It comes from the size of drops, the surfaces they touch, the frequencies they produce, the way continuous sound masks sudden noise, the way the pattern changes without becoming alarming, and the way shelter changes the meaning of weather. A raindrop that began in a cloud now becomes part of a soundscape. It falls through air. It reaches the world. It strikes the surface. Its energy becomes vibration. That vibration moves through air as sound. The ear receives it, the brain places it in the background, and slowly, the room feels softer. Outside, rain continues to fall on roofs, leaves, roads, soil, rivers, and windows. Each surface changes it. Each impact adds a tiny note. Together, the drops create a broad, gentle sound. A natural mask, a soft texture, a moving background, not silence, but something kinder than silence. A sound with no sharp edges. A sound that can cover the small noises of the night. A sound that can make the world feel farther away. And after the rain has fallen for a while, another quiet form of water may appear. Near the ground, between trees, above fields, across valleys. Not falling from clouds, but hanging in the air. A low, pale cloud touching the surface of the earth. Mist. Mist is one of the quietest forms of water in the air. It does not fall like rain. It does not gather high above us like a cloud. It stays close to the ground. It softens the edges of trees. It hides the far side of a field. It turns a lake into a pale mirror. And it can make the world feel slower, even when the science behind it is very precise. Mist and fog are both made of tiny water droplets suspended in the air near the surface of the earth. In that sense, they are similar to clouds. A cloud is a collection of tiny droplets or ice crystals suspended in air. Fog is essentially a cloud at ground level. Mist is also a near-ground suspension of tiny droplets, but it is usually thinner. The difference between mist and fog is often based on visibility. In many meteorological definitions, fog reduces horizontal visibility to less than 1 kilometer. Mist reduces visibility, but not as much. So fog is denser, mist is lighter. Both are made from the same basic idea. Water vapor cools. The air reaches saturation. Tiny droplets form, and the invisible becomes visible near the ground. The ground is important here. Unlike most clouds, which form above us as air rises and cools, mist and fog often form because air near the surface cools directly. During the day, the ground absorbs energy from sunlight. After sunset, the ground begins to lose heat. It radiates energy away into the sky. On clear nights, this cooling can be especially strong because there are fewer clouds to trap outgoing heat near the surface. As the ground cools, it cools the air just above it. If that air contains enough water vapor, and if it cools to its dew point, condensation begins. The dew point is the temperature at which air becomes saturated with water vapor. When air cools to the dew point, it can no longer hold all of its water vapor in gas form. Some of that vapor condenses into liquid droplets. If the droplets form on grass, leaves, cars, roofs, or windows, we call it dew. If the droplets form suspended in the air near the ground, we call it mist or fog. This is one of the main ways radiation fog forms. Radiation fog often appears on calm, clear nights. The ground loses heat. The air near the ground cools. Moisture condenses. A shallow layer of fog begins to develop. It may be especially common in valleys, near rivers, over wet soil, or in places where the air is already humid. Wind matters. If there is too much wind, the cooling near the ground may be mixed away. The air does not remain still enough for a fog layer to form, but if the air is completely still, the fog may remain very shallow. A light breeze can sometimes help by mixing moisture through a slightly deeper layer. So fog often prefers a delicate balance, calm enough for cooling, slightly mixed enough to spread the droplets, moist enough to reach saturation, cool enough to condense. This is why fog can feel mysterious, even though its ingredients are ordinary. A little cooling, a little moisture, a quiet night, a layer of air close to the ground. The fog appears not because the world has changed suddenly, but because temperature and moisture have crossed a small threshold. The same air that was clear an hour before can become visible, not because new water has arrived, but because the water vapor already present has condensed into droplets. This is an important point. Fog does not require rain. It does not require a storm. It does not require clouds overhead. It can form from the water vapor already near the surface. The atmosphere simply cools enough to reveal it. Radiation fog is common in low-lying areas. Valleys are especially good places for it. At night, cold air tends to drain downhill because it is denser than warm air. It collects in low places. Moisture may also be present near streams, wet fields, lakes, or soil. As the cold air settles into a valley, fog can form there while higher slopes remain clear. From above, a valley filled with fog can look like a quiet white river. From inside, it can feel like walking through a low cloud. Edges soften, distance becomes uncertain. Sound may feel slightly muted. Light spreads more evenly. The world becomes less sharp. There are several types of fog, and each forms through a slightly different process. Radiation fog forms by a cooling of the ground and the air near it. Advection fog forms when moist air moves over a cooler surface. The word advection means horizontal movement of air. If warm, moist air passes over cold land or cold water, the lower part of that air can cool to its dew point. Condensation begins. Fog forms. This can happen along coastlines where moist marine air moves over colder ocean currents or chilled land. It can also occur when warm air moves over snow-covered ground. The air is carrying moisture. The surface cools it from below. Fog appears. Advection fog can be thicker and more persistent than radiation fog because it is supplied by moving air. As long as moist air continues to pass over the cold surface, fog can keep forming. This is one reason some coastal places are famous for fog. The ingredients repeat: moist air, cold water, horizontal movement, condensation near the surface. Another type is evaporation fog, sometimes called steam fog. This happens when cold air moves over warmer water. Water evaporates from the warm surface into the colder air above. The cold air quickly becomes saturated. Tiny droplets form. The result can look like steam rising from a lake, river, or ocean. It is not steam in the boiling water sense. It is fog formed by evaporation into cold air. You might see this over a lake on a cold morning. The water is warmer than the air. Moisture rises. The air just above the surface becomes saturated. Wisps of fog drift upward. This type of fog can be very beautiful, but the science is simple. Warm water adds vapor to cold air. The cold air cannot hold much vapor. Condensation occurs. A pale layer forms above the surface. Upslope fog forms when moist air is forced to rise along sloping terrain. As the air rises, it expands and cools. If it cools to the dew point, fog or low cloud can form along the slope. This is common near hills and mountains when moist air moves steadily upward. From a distance, it may look as if a mountain is wearing a cloud. From inside it, the cloud is fog. Again, the difference between fog and cloud depends mostly on where the observer is. If the droplets are above you, you call it cloud. If you are inside them at ground level, you call it fog. This means that fog is not a separate substance from cloud. It is the same type of suspended droplets in a different position. A low cloud touching a mountain becomes fog for someone standing on the mountain. A fog layer seen from a hilltop may look like a cloud sea below. The terms depend on perspective. The water droplets themselves do not know whether we call them cloud, fog, or mist. They are simply droplets, suspended in air. Fog droplets are usually very small, often around 1 to 20 micrometers in diameter. Because they are so tiny, they fall very slowly. They can remain suspended by weak air movements. This is why fog does not fall like rain. The droplets are too small to descend quickly. Instead, they drift. They collect on surfaces. They merge with other droplets. They evaporate if the air warms or dries. They can wet the world without producing rainfall. Walk through dense fog, and your hair or clothing may become damp. Leaves may gather droplets. Spiderwebs may become outlined in tiny beads. Grass may shine. Metal surfaces may become wet. This moisture is not falling as raindrops. It is being deposited from droplets suspended in the air. The fog touches surfaces, and the droplets collect. This is called fog deposition. In some ecosystems, especially coastal forests and mountain regions, fog can be an important source of water. Plants can capture fog droplets on leaves, needles, or branches. The water may drip to the ground. In very foggy environments, this can add meaningful moisture to the ecosystem. Some forests receive a significant part of their water from fog drip. This is another quiet way the atmosphere gives water to the land, not as rain, not as snow, but as suspended droplets touching leaves. Mist is usually thinner than fog. It may allow the far side of a field to remain visible. It may blur a road without hiding it. It may hover over a river at dawn. It often gives the air a silvery quality. In meteorology, the difference is practical. How far can you see? If visibility is reduced strongly, it is fog. If visibility is reduced only moderately, it is mist. But in ordinary language, people often use the words more loosely. Mist sounds lighter. Fog sounds denser. Haze is different. Haze is often made of dry particles, such as dust, smoke, pollution, or salt. rather than primarily water droplets. Haze can reduce visibility too, but its cause is not the same. Mist and fog are mostly about condensed water. Haze is often about particles. Smog is another related word. It originally combines smoke and fog. Today, it often refers to air pollution that reduces visibility and affects air quality. So when we talk about mist and fog in this calm water cycle, we are focusing on droplets of water near the surface. The clean, physical process of condensation. The air cools, the vapor condenses, the droplets scatter light, visibility changes. One reason fog looks pale or white is that the droplets scatter light in many directions. A single tiny droplet is too small to notice, but billions of droplets together scatter enough light to make the air look milky. The same general idea explains the whiteness of clouds. Water droplets and ice crystals scatter sunlight. In fog, this scattering happens all around the observer. You are inside the scattering medium. Light from lamps, headlights, the moon, or the sun spreads through the droplets. At night, fog around streetlights can create glowing halos. In the morning, sunlight through fog can look soft and diffused. Shadows become weak. Colors become muted. Distances become compressed. This is not only visual poetry, it is optics. Tiny droplets redirecting light. Fog also affects sound, though not always in the way people imagine. The droplets themselves do not simply make sound disappear, but fog often forms in weather conditions that also influence sound. Kamsash air. Temperature inversions, moisture near the surface. The temperature inversion happens when cooler air is near the ground and warmer air sits above it. Normally, air gets cooler with height in the lower atmosphere, but during an inversion, the pattern is reversed near the surface. Inversions can trap cool, moist air low to the ground and help fog persist. They can also affect how sound travels. Sound may bend or carry differently depending on temperature layers and wind. This is one reason foggy nights can feel acoustically unusual. Distant sounds may seem muffled or, in some conditions, may carry farther. The atmosphere is layered. Light and sound both respond to those layers. Fog usually disappears when the air warms, dries, or mixes. After sunrise, sunlight warms the ground. The ground warms the air near the surface. Warmer air can hold more water vapor. The tiny droplets begin to evaporate. The fog thins. Edges return. The far trees appear. The road becomes clear. The cloud at ground level becomes invisible vapor again. This is called fog lifting, or burning off. Though burning is only a phrase, the fog is not burned, it evaporates. Sometimes fog lifts into low stratus cloud before disappearing. Sometimes it breaks into patches. Sometimes it remains all day if the air stays cool, moist, and stable. The life of fog depends on the balance of cooling, warming, moisture, and mixing. If the ground stays cold, the fog may persist. If dry air moves in, it may evaporate quickly. If wind increases, it may mix away. If sunlight is strong enough, it may thin and vanish. Fog is delicate. It exists near a boundary. Slightly cooler, and droplets form. Slightly warmer, and they disappear. This makes fog one of the clearest examples of how small temperature changes can transform the air. The difference between clear air and fog may be only a few degrees, sometimes less. The water is already present. The atmosphere is simply waiting for the right point. Mist, fog, dew, and low clouds are all close relatives. Dew forms on surfaces. Fog forms in the air near surfaces. Low stratus forms just above the ground. Mist is a lighter version of near-ground droplets. All of them happen when water vapor returns to liquid form. All of them depend on cooling and saturation. All of them reveal moisture that was previously invisible. This connects scene 8 back to the larger water cycle. Evaporation sent water upward. Condensation made clouds visible. Some clouds formed rain, and near the ground, the same physical process can create mist. A quiet layer of droplets, a cloud at walking height, a soft pause between air and water. In a way, mist is the atmosphere whispering that it is full of moisture. Not enough to rain, not lifted high enough to become a sky cloud, just cool enough and moist enough to show itself near the surface. It may gather above a lake, it may fill a valley, it may wrap itself around trees, it may drift across a field before sunrise. Then, as the day warms, it may disappear. But disappear is not quite the right word. Just as with evaporation, the water is not gone. it has changed form again. The droplets become vapor. The vapor mixes into the air warms, the world clears, and the same water may later rise higher, cool again, and join another cloud. This is the quiet continuity of the water cycle. No form is final. Rain can become groundwater. Groundwater can become a spring can become a stream can become vapor can become cloud can become mist can become vapor again. And sometimes, when temperatures fall far enough, the same atmospheric water takes on colder forms: snow, ice, hail, freezing rain. The next part of our journey moves into the cold layers of the atmosphere, where droplets freeze, crystals grow, and falling water becomes something other than rain. Not every drop of water reaches the ground as rain. Sometimes the atmosphere is cold enough to change the journey. A particle that begins as a tiny cloud droplet may freeze. A growing ice crystal may become a snowflake. A falling snowflake may melt into rain. Rain may fall through cold air near the surface and freeze on contact. Or a small ice particle may travel up and down inside a storm cloud, collecting layer after layer of frozen water until it becomes hail. All of these forms are part of the same water cycle. Rain, snow, sleet, freezing, rain, hail. They are not separate worlds. They are different outcomes of temperature, moisture, cloud structure, and vertical air motion. The most important idea in this scene is that the atmosphere has layers. The air near the ground may be warm, while air above it is cold. Or the ground may be cold, while a warmer layer sits above. Or the whole column of air from cloud to surface may remain below freezing. Precipitation falls through these layers, and as it falls, it changes. This is why surface temperature alone does not always tell us what kind of precipitation will reach the ground. A thermometer near the ground may say one thing, but the falling particle experiences the entire column of air above it. From the cloud base to the surface, through cold layers, warm layers, dry layers, moist layers, and each layer can change its form. Let us begin with snow. Snow forms when water vapor becomes ice inside a cold cloud. In very cold air, water vapor can deposit directly onto an ice crystal. This means it changes from vapor into solid ice without becoming liquid first. The process is called deposition. An ice crystal begins around a tiny particle, often called an ice nucleus. Not every particle can start ice formation. Some materials are better ice nuclei than others. Dust, mineral particles, biological particles, and other aerosols can sometimes help ice crystals begin. Once a small ice crystal exists, water vapor can deposit onto it. The crystal grows. Its shape depends strongly on temperature and humidity. This is why snow crystals can have many forms: plates, columns, needles, dendrites, stellar shapes, simple prisms, complex branches. The famous six-sided structure of many snowflakes comes from the molecular arrangement of ice. Water molecules in ice form a hexagonal crystal lattice. This six-fold symmetry appears in the shapes of many snow crystals, but no two snowflakes grow under exactly the same path through the cloud. As a crystal falls, it passes through changing temperatures and humidity levels. One region may favor flat plates, another may favor branching arms, another may add small side branches. The final snowflake is a record of its journey through the cloud, a tiny history written in ice. Snowflakes can also grow by colliding and sticking together. This is called aggregation. When snowflakes fall through air that is near freezing, their surfaces may become slightly sticky. They can join with other flakes. This creates larger, fluffier snowflakes. That kind of snow often falls gently, with large flakes visible in the air. In colder, drier air, snow crystals may remain smaller and more powdery. So the texture of snowfall depends on the temperature and moisture inside the cloud and below it. If the entire layer of air from cloud to ground remains below freezing, snow can reach the surface without melting. The snowflake falls from the cloud. It passes through cold air, it remains ice, and it lands as snow. But if the snowflake falls into a warm layer, it may begin to melt. This melting layer is important. Meteorologists often pay attention to the freezing level, the height where air temperature crosses 0 degrees Celsius. Above that level, temperatures are generally below freezing. Below it, temperatures may be above freezing. If a snowflake falls through a deep enough warm layer, it melts completely and becomes a raindrop. This is a very common path for rain. Rain at the ground may have begun as snow high in the cloud. The snow melted as it fell. By the time it reached the surface, it was liquid water. This is why rain can have an icy beginning. But sometimes, the temperature layers are more complicated. Suppose snow forms high in a cloud, it falls into a warm layer and melts into liquid rain. Then, near the ground, it enters a deep layer of cold air below, freezing. If that cold layer is deep enough, the raindrop can freeze again before it reaches the surface. It becomes a small ice pellet. This is often called sleet in the United States, or ice pellets in meteorological language. The particle begins as snow, melts into rain, then freezes again before landing. Because it freezes while falling, it reaches the ground as a small, hard pellet of ice. Ice pellets can bounce when they hit the surface. They may sound like tiny beads tapping on windows, roofs, or pavement. The sound is different from snow, sharper, more granular, more like small grains striking a surface. The key requirement is a warm layer aloft, deep enough to melt snow, followed by a cold layer near the ground, deep enough to refreeze the drops. Now consider another possibility. Snow forms high in the cloud. It falls through a warm layer and melts into rain. Then it enters a shallow layer of sub-freezing air near the ground. The cold layer is not deep enough to freeze the raindrop while it is still falling, so the drop remains liquid as it reaches the surface. But the surface is below freezing. The drop freezes when it touches the ground, a tree branch, a power line, a road, or a window. This is freezing rain. Freezing rain is one of the most dangerous forms of winter precipitation because it can coat surfaces with clear ice. The falling drops are liquid, but the surfaces they touch are cold enough to freeze them. A thin glaze of ice can form. It may look smooth and transparent. It can make roads slippery. It can weigh down branches and wires. In our calm explanation, we do not need to dwell on the danger, but the physics is important. Freezing rain requires a warm layer above and a shallow cold layer near the surface. The particle melts. It does not refreeze in the air. It freezes on contact. This is different from sleet. Sleet freezes before reaching the ground. Freezing rain freezes after reaching the ground. A small difference in the depth of the cold layer can decide between them. A few hundred meters of cold air can matter. A slight change in temperature can matter. The vertical profile of the atmosphere determines the precipitation type. This is why winter weather forecasting can be difficult. The difference between rain, snow, sleet, and freezing rain may depend on thin layers of air above the ground, not just what is happening at eye level, not just whether the surface feels cold. The whole column matters. Now, let us look at hail. Hail is different from sleet and freezing rain. It usually forms in strong convective clouds, especially cumulonimbus clouds. These are clouds with powerful updrafts. Inside a thunderstorm, air can rise rapidly. Small ice particles or frozen droplets can be carried upward into colder regions of the cloud. There, they collide with supercooled water droplets. Remember, supercooled droplets are liquid water droplets below freezing temperature. When these droplets hit an ice particle, they can freeze onto it. This adds a layer of ice. The particle grows. If the updraft is strong enough, it can keep the growing hailstone suspended or carry it upward again. The hailstone may move through different parts of the cloud. Some regions contain more liquid water. Some are colder. Some have stronger updrafts. As the hailstone travels, it collects more supercooled droplets. The droplets freeze. Layer by layer, the hailstone grows. This process is called accretion. Sometimes the freezing is quick and traps tiny air bubbles, creating cloudy white ice. Sometimes the freezing is slower, creating clearer ice. This can produce layers inside a hailstone, a little like rings. If you cut a hailstone open, you may see evidence of its growth history. A hailstone falls when it becomes too heavy for the updraft to support. The stronger the updraft, the larger the hailstone can become before falling. This is why large hail is associated with strong thunderstorms. Hail is not simply frozen rain. That is a common misunderstanding. Frozen rain that refreezes before reaching the ground is sleet, or ice pellets. Hail forms inside convective storm clouds through repeated growth of ice in strong updrafts. Its story is more vertical, up, down, sideways, up again, to regions of supercooled water and ice. A hailstone is a product of cloud dynamics, not just a raindrop that got cold. Graupel is another icy form worth mentioning. Graupel forms when snowflakes or ice crystals collect supercooled droplets that freeze onto them. The result is a soft, rounded ice particle. It is sometimes called soft hail or snow pellets. Graupel is usually smaller and more fragile than hail. It can look like tiny white pellets. It forms by rimming, the freezing of supercooled droplets onto ice. Rimming is also important in hail growth. but hail usually involves stronger updrafts and more layering. So there is a family of frozen precipitation. Snow crystals grow by deposition of vapor onto ice. Snowflakes can aggregate by sticking together. Rimed snow can become graupel. Ice pellets form when melted snow refreezes during its fall. Freezing rain forms when melted snow remains liquid until it freezes on contact with a cold surface. Hail forms in strong storm updrafts through repeated collection and freezing of supercooled droplets. The atmosphere has many ways to shape falling water. Temperature is the first key. Moisture is the second. Air motion is the third. The fourth is time. How long does a particle spend in a cold layer? How long in a warm layer? How long inside the cloud? How long in an updraft? How much time does it have to grow, melt, freeze, or collect other droplets? Precipitation is not only about what a particle is, it is about where it has been. A snowflake has passed through cold, moist air. A raindrop may have melted from snow. A sleet pellet has melted and a freezing raindrop has melted, remained liquid, and frozen on contact. A hailstone has traveled inside a storm cloud, growing in layers. Each form carries a small atmospheric biography. The shape of falling water tells us something about the air above. This is why meteorologists use soundings. A sounding is a vertical measurement of the atmosphere, often taken by a weather balloon. From this information, meteorologists can see the layers that precipitation will pass through. A below freezing layer near the ground, a warm layer above it, a deep cold column, a moist layer, a dry layer, a strong wind shift. The atmosphere becomes a vertical map, and that map helps explain what reaches the ground. If the entire profile is below freezing and moist, snow is likely. If snow falls into a deep warm layer and the surface is above freezing, rain is likely. If there is a warm layer aloft and a deep cold layer near the ground, sleet may form. If there is a warm layer aloft and only a shallow cold layer near the surface, freezing rain may occur. If strong convective updrafts are present with supercooled water, hail can form. This is the technical heart of precipitation type. Not just cloud, not just ground, but the whole vertical path. In a calm winter scene, it may look simple. Snow falls through a street lamp, branches become white. The ground becomes quiet. But above that scene, the atmosphere has arranged itself in a particular way. Cold enough from cloud to ground, moist enough for crystals to grow, gentle enough for flakes to survive. In another place, rain may fall onto freezing branches and become a transparent glaze. The surface is cold, the rain is liquid. The freezing happens on contact. In another place, tiny ice pellets may tick against a window because drops refroze while falling. In another, a thunderstorm may build a hailstone in rising air. All are water, all are weather, all are part of the same cycle. The difference lies in form and path. When we return to the sound of a quiet rain, it can be easy to forget these colder possibilities. But clouds are full of phase changes. Vapor becomes liquid. Liquid becomes ice. Ice becomes liquid. Liquid becomes vapor. Water moves between forms depending on temperature and pressure. It is flexible, responsive, constantly changing. The cloud is not only a place where droplets gather, it can also be a place where crystals grow, melt, freeze, collide, and fall. And each version of falling water changes the world below in a different way. Snow softens sound, rain darkens surfaces, sleet taps and bounces, freezing rain coats and shines, hail strikes with sudden force. These differences begin above us, in layers of air we usually cannot see. A few degrees here, a warm layer there, a strong updraft, a cold surface. A supercooled droplet, an ice nucleus, small conditions, arranged vertically, create very different outcomes. This is why the science of precipitation is both delicate and powerful. It depends on details, and those details fall from the sky. As rain, as snow, as ice, as something between. The next time cold rain touches a window, it may be worth remembering that above the roof, above the street, above the low clouds, water may have taken several forms before arriving. It may have been vapor, then ice, then snow, then liquid, then perhaps ice again. The journey is rarely as simple as it looks from the ground. And after exploring these colder forms, we can turn to one of the gentler optical effects of water in the air. A moment when falling droplets do not only make sound, or soak the ground, or freeze into crystals, they bend sunlight, they separate colors, and they create a quiet arc across the sky, a rainbow. After rain, when sunlight returns at the right angle, the falling drops can create one of the most recognizable patterns in the sky, a rainbow. A rainbow is not an object hanging in the air. It is not a colored bridge. It is not something that exists in one fixed place. It is an optical effect created by sunlight, raindrops, and the position of the observer. For a rainbow to appear, sunlight usually comes from behind you, while raindrops are in the air in front of you. The light enters each drop. Inside the drop, it slows and bends. This bending is called refraction. Light changes direction when it passes from air into water because light travels at a different speed in water than in air. Sunlight looks white to us, but it contains many wavelengths of light. Different wavelengths bend by slightly different amounts. Red light bends a little less. Violet light bends a little more. This separation of colors is called dispersion. After entering the raindrop, the light reflects from the back inner surface of the drop. Then it exits the drop and bends again as it passes from water back into air. So a primary rainbow involves three main steps inside many droplets: refraction as light enters, reflection inside the drop, and refraction again as light leaves. The colors spread apart. The observer sees light coming from many droplets at particular angles. For the primary rainbow, the strongest light reaches the observer at about 42 degrees from the direction opposite the sun. This angle is why rainbows appear as arcs. Each color reaches the eye from droplets positioned along a different part of that geometry. The drops themselves are not colored permanently. A drop that sends red light to one observer may send a different color to another observer in a different position. This means every rainbow is partly personal. Two people standing apart are not seeing the exact same set of droplets. They are seeing light from different drops, arranged by their own viewing position. The rainbow belongs to the observer as much as it belongs to the rain. This is one of the quiet details that makes rainbows interesting. They feel like distant objects, but they are really relationships. Sun, water, angle, eye. The sky becomes a geometry of light. Sometimes, outside the primary rainbow, a second fainter rainbow appears. This is called a secondary rainbow. It forms when light reflects twice inside the raindrop before leaving. Because of this extra reflection, the colors are reversed. In the primary rainbow, red is usually on the outside and violet on the inside. In the secondary rainbow, the order is reversed. The secondary rainbow is also dimmer because more light is lost during the extra reflection. Between the primary and secondary rainbow, the sky may appear darker. This darker region is called Alexander's band. It happens because less light is directed toward the observer from that part of the sky. Even the space between rainbows has an explanation. A rainbow is not only beauty, it is optics, it is geometry, it is the behavior of light inside water. Small drops can produce softer, paler rainbows. Larger drops often create brighter, more vivid colors. If the droplets are very tiny, as in mist or fog, the colors may become weak or almost white. A fog bow can form in fog, but because the droplets are so small, the colors overlap strongly and the bow appears pale, sometimes nearly white. This connects the rainbow back to mist. Same sunlight, same water, different droplet size, different visual result. Rainbows are usually seen when the sun is low in the sky. Early morning or late afternoon are good times because the sunlight comes in at a lower angle. If the sun is too high, the rainbow may be below the horizon and difficult or impossible to see from the ground. This is another reminder that a rainbow is not simply where rain is. It depends on position. The sun must be behind you. The rain must be ahead. The angle must be right, and the droplets must be present in the air. After a rainfall, the world often contains all the ingredients. Wet ground, clearing clouds, low sunlight, drops still falling somewhere in the distance. Then, for a short time, the water that had been moving invisibly through the cycle becomes a lens for color. Earlier in this journey, water rose as vapor. It cooled into clouds, it grew into droplets. It fell as rain, it struck surfaces and became sound. It gathered near the ground as mist. It froze into crystals, pellets, or ice. And now, in this quiet optical moment, it bends light. The same substance appears again in a different role, not as weather only, not as sound only, not as moisture only, but as a prism. Each raindrop becomes a tiny optical instrument. Most of the time, we do not notice this. Rain falls, light passes, drops vanish into soil or rivers. But when the geometry is right, the hidden physics becomes visible. The sky shows the path of light, the colors separate, and a soft arc appears for a while before fading. A rainbow is temporary because its conditions are temporary. The sun moves, the rain shifts, the droplets fall, the air clears, the observer moves, the angle changes, and the colors disappear. But the water remains. Some of it lands on leaves, some lands on roads, some enters streams, some sinks into soil, some evaporates again. The rainbow fades, but the cycle continues. And now, after following water through clouds, rain, sound, mist, ice, and light, we can let the journey return to the ground, to the quiet places where rain goes after it falls. After rain reaches the ground, its journey does not end. The fall is only one part of the cycle. A drop may land on a leaf. It may strike a roof. It may darken a stone. It may disappear into grass. It may join a thin line of water moving along the side of a road. It may sink into soil. It may enter a stream, or it may return to the air before traveling very far at all. Once rain reaches the surface, several paths become possible. Some water becomes runoff. Runoff is water that flows over the land surface. It moves downhill because of gravity. It gathers in small channels. It enters gutters, ditches, streams, and rivers. In natural landscapes, runoff may move across leaves, roots, rocks, and soil. In cities, it may move across rooftops, pavement, concrete, and drains. The surface matters. If rain falls on bare rock, compacted soil, or pavement, more of it may run off quickly. If rain falls on loose soil, forest floor, grassland, or wetlands, more of it may slow down and soak in. This soaking movement is called infiltration. Infiltration is the process by which water enters the soil. At first, the water fills small spaces between grains of soil. Sand has relatively large spaces. Clay has much smaller spaces. Organic matter roots, tunnels made by insects and worms, and cracks in the ground can all influence how easily water enters. Healthy soil often acts like a sponge. It receives rain, it holds part of it, it lets part of it move downward, and it releases part of it slowly over time. This is one reason vegetation matters. Leaves slow the impact of falling rain. Roots help create pathways in the soil. Plant material on the surface protects the ground. Moss, fallen leaves, grasses, and roots can reduce rapid runoff and help water enter the land more gently. A forest does not only receive rain, it changes the way rain arrives. Some drops are caught by leaves and branches. This is called interception. Intercepted water may evaporate back into the air, or it may drip slowly from leaf to leaf, or it may run down stems and trunks toward the ground. By the time rain reaches the forest floor, it has often been delayed, softened, and redistributed. The canopy turns a direct fall into a slower descent. This affects erosion. When heavy rain strikes bare soil directly, it can break apart soil aggregates and loosen particles. Those particles may be carried away by runoff. This process is part of erosion, but when plants, leaf litter, roots, and moss protect the surface, the rain's impact is reduced. Water still moves, but it moves with less force. The land has more time to absorb it. Below the surface, water continues to travel. Some infiltrated water remains in the upper soil, where plant roots can reach it. Plants draw this water upward. They use it in their tissues. They release some of it back to the atmosphere through transpiration. This means that rain falling into soil may later leave through leaves, soil to root, root to stem, stem to leaf, leaf to air. A quiet upward path after the downward fall. Some water moves deeper. It passes below the root zone. It travels through layers of soil, sand, gravel, and fractured rock. This downward movement is called percolation. If it reaches a zone where the spaces in rock or sediment are filled with water, it becomes part of groundwater. The top of this saturated zone is called the water table. Groundwater moves slowly compared with rivers. Sometimes very slowly. It follows the slope of underground pressure and geology. It may move through pores in sandstone, through cracks in limestone, through gravel beds, through ancient layers beneath fields and towns. Some groundwater may return to the surface as springs. Some may feed streams during dry weather. This is called base flow is one reason a stream can keep flowing even when it has not rained recently. The water in the stream may partly come from rain that entered the ground days, weeks, months, or even years earlier. Rain can also enter lakes and wetlands. A lake receives water from direct rainfall, from streams, from groundwater, and from surrounding land. It loses water through outflow, evaporation, and sometimes seepage into the ground. A wetland holds water close to the surface. It slows flow. It stores moisture. It supports plants, insects, birds, microbes, amphibians, and many small forms of life. Wetlands can act as natural buffers. They can hold rainwater during wet periods and release it slowly. They can trap sediment. They can filter some pollutants. They can reduce the speed of water moving through a landscape. In this way, where rain goes after it falls is not only a matter of physics, it is also ecology. The path of water shapes habitats. A puddle may become a temporary world for tiny organisms. A soaked leaf layer may awaken fungi and microbes. A stream may rise and carry nutrients downstream. A wet meadow may become active with roots and insects. Rain changes the surface chemistry of the world. It dissolves minerals, it carries organic matter, it moves particles, it brings oxygen into soil spaces. It helps transport nutrients. Even the smell after rain is connected to chemistry and biology. One familiar scent is called petrol. It often comes from oils released by plants and compounds produced by soil microbes, especially a compound called geol. When raindrops hit dry soil, tiny air bubbles can rise and burst, releasing small particles and aromatic compounds into the air. This is part of why the first rain after a dry period can have such a distinct smell. The sound of rain, the sight of rain, and even the smell of rain are all connected to physical processes, impact, evaporation, aerosols, soil, microbes, plant oils. Water touches the ground, and the ground answers. Some rain returns to the atmosphere quickly. A drop on warm pavement may evaporate soon after the shower ends. Water caught on a leaf may evaporate before reaching the soil. A thin film on glass may disappear into indoor or outdoor air. Some rain returns more slowly. Water in a lake may remain for months or years. Water underground may wait much longer. Water in snowpack may stay frozen until spring. Water in glaciers may remain locked away for vast spans of time. The water cycle has fast paths and slow paths. A drop may rise again tomorrow, or it may not return to the air for many years. Both are part of the same system. This is one reason the water cycle is better imagined, not as a simple circle, but as a network. A branching, changing, layered system. Atmosphere to rain, rain to leaf, leaf to soil, soil to root, root to air, rain to stream, stream to river, river to sea, sea to vapor, vapor to cloud. There are many roots, many pauses, many returns. And every rainfall chooses some of them. The rain that falls on a mountain may become snowmelt. It may feed a river that travels hundreds of kilometers. The rain that falls on a city may enter a storm drain within minutes. The rain that falls on a forest may be held in moss, leaves, and soil. The rain that falls on a desert may vanish quickly into dry ground or evaporate under the sun. The rain that falls on a lake may become part of the lake's quiet surface. Each landscape receives rain differently. The science is the same. Gravity, energy, temperature, soil, structure, porosity, permeability, evaporation, condensation, flow, storage, but the story changes with place. By now, we have followed water through many forms. We began with the planet's water, the oceans, rivers, ice, soil, atmosphere, and living world. We watched water become invisible through evaporation. We followed vapor upward into cooler air. We saw clouds begin through condensation. We learned how cloud shapes reveal the structure of the atmosphere. We watched tiny droplets grow into raindrops. We listened to the physics of rain sound. We came down to the ground with mist and fog. We entered the cold layers, where snow, hail, sleet, and freezing rain form. We watched sunlight bend inside droplets and become a rainbow. And now, we have returned to the surface, to soil, streams, roots, rivers, lakes, groundwater, and the quiet places where rain continues after the fall. This is the shape of the water cycle, not a perfect circle drawn neatly on a page, but a moving planet, a system of air, ocean, land, ice, and life. Water rises, water cools, water gathers, water falls, water flows, water waits, water returns, sometimes quickly, sometimes slowly, sometimes visibly, sometimes hidden underground or held in ice. The rain outside a window may seem small, a sound in the dark, a pattern on glass, a soft tapping on a roof, but it belongs to something much larger. It belongs to warm oceans and cold clouds, to invisible vapor and tiny aerosols, to crystals, droplets, rivers, roots, and stones, to sunlight, to gravity, to the shape of the land, to the slow breathing of the atmosphere. And perhaps this is why rain can feel so calming. It is movement without hurry, change without sharp edges, a reminder that the world continues in quiet cycles, whether or not we watch every pot. A drop falls, another follows. Somewhere, mist gathers near the ground. Somewhere, a cloud begins to form. Somewhere, sunlight warms the ocean. Somewhere, water slips into soil. Somewhere, a stream carries old rain toward the sea. And somewhere, even now, A future raindrop is rising invisibly into the air. There is no need to follow it all. There is no need to remember every detail. You can let the cycle continue without holding it in your mind. The rain will keep moving. The clouds will keep forming. The mist will come and go. The rivers will find their way. And the water will return again and again in its own quiet time. Thank you for spending this calm journey with Midnight Science. If you are still awake, you can let the final sounds of rain stay with you for a while. Let the room become quiet. Let the outside world grow soft. And let the story of water drift into the background. Good night.